first time wearing this microphone. I feel like I'm a K-pop star now. Anyway, yeah, so really nice to meet you. I'm Leo Jeong. I'm a senior research engineer at Linea. And today I'm going to talk about how to optimize ZK-EVM provers. So this is the outline of today's talk. I will talk about the motivation and also the introduction of this talk. I will share how to optimize ZK-EVM provers based on our more than 1 year of our optimization experience. Then we'll conclude the talk. So first time, so this is the initial challenge and problems we had. So Linea launched our mainnet last year, August, and we were so happy. So we were kind of dancing all the time. But we realized that prover was really slow. So we were like, what's going on here? And we were spending a lot of money for provers. So we thought it's a huge problem, and we decided to optimize it. So what we did is for more than 1 year, we spent a lot of time and effort optimizing prover in production. So that picture, that's actually me fixing and optimizing prover in production. So your prover is running mainnet, and you need to fix it. That's what I did. But luckily, we were able to reduce the prover runtime by almost 75%, which is good. So today, that's the main content that I'm going to share today. First of all, let's talk about why it's important to optimize ZK-EVM prover. The first thing is, of course, money. This is one of the biggest cost contributors in ZK rollups. And prover optimization directly means you can reduce the operating cost of your ZK project, so which is very important. The second, the performance impact. So when you optimize ZK prover, that means you have less runtime of your prover, which also means you have faster verification and finalization. And in that way, you can improve your TPS, right? And your users will be happy. And lastly, you can also improve your scalability by optimizing ZK prover, because you can support more transactions, which means you can handle more complex proofs as well. So let me share some common bottlenecks here. So most ZK-EVM provers and projects, they have really high complexity. So inherently, I mean, ZK-EVMs are very complex because we want to kind of simulate EVMs, right? And we want to provide the full compatibility. So every project has their own design, their architecture, so it's really hard to optimize. But all the projects, they're something in common. They have high resource consumptions, right? So CPU and memory, they're using a lot of CPU and memory, and also because to support large-scale cryptographic calculations. So we have these things in common. So the common bottlenecks is you have CPU usage and parallelization issues, probably. And then you will have memory overhead a lot. And you will have I/O bottlenecks because you are dealing with a huge amount of data. So this talk, I will talk about what we will cover and what will not be covered. So first time, we will not cover Linea-specific optimizations because, you know, if I share that kind of information, you can't apply that to your project. So I'm not going to talk about detailed cryptographic theory behind our project or ZK-EVM. And also, I will not share about hardware accelerated optimizations. And then we'll focus on CPU optimizations. So here, I will cover some quick wins and strategies. So you can just pick up and apply to your project in a week or 2 weeks, or sometimes maybe on the flight going back to your home, you can actually apply that easily. And then I will share mostly on CPU and memory optimizations without any significant changes on your architecture or on your code. So that was the intro. I will share about the problems right now and how to actually optimize it. The first thing you have to do is you need to know your code, right? So there's a really famous quote in this programming world. which is premature optimization is really bad. Let's just don't do that. Because, sometimes you want to optimize your code because, it feels fun. So you just optimize it. And because you think it's going to be the bottleneck, but most cases it's not. So before you actually start optimizing your code, you need to find out the problems first. And the most common way or easiest way to do that is using CPU and memory profiling. So most languages, they have kind of built-in profiling tools so that you can visualize your CPU or memory usage, and you can understand your code there. In our case, we are using Golang. We are based in, so we used that tool, the profiling tool, to visualize our program. So this is the CPU and memory profiling we actually had. This is the whole life cycle of our prover. So I know what you are thinking right now. You're like, oh no, I'm gonna just sleep for 20 minutes, wake me up in 20 minutes. But don't worry, yeah. We spent a lot of time, and then we kind of categorized them for you, and we'll share that quickly today. So here you can see many holes or sparse areas, which is white colored. So here, the green color means you are using CPU very extensively, so you're good. But white colors, that means something is wrong. So mostly, it means CPU is underutilized. So you find out which part is not being used fully, and then you go into the code, and you look at the code, and you can fix it. And on top of that, we have memory usage patterns. And the main goal of memory usage or memory optimization is to reduce the memory peaks. So first time, I will talk about CPU, and then we'll move to memory. So you have many different CPU issues, but mostly it's going to be two cases. The first one is poor parallelization, and then the second one is CPU underutilization. The first pattern, when you look at this graph, here you have CPU number 1 to maybe CPU number 100. And we are using only 5 CPUs actively, and the others are just doing nothing. So we realized in many cases we have these issues. So we had to add more parallelization to improve that. The second one is you are actually using 100 CPUs, but between some runtimes, you are waiting for something. So that means you are underutilizing your CPU. The first thing, so how to improve parallelization, it is a common methodology that you can apply to your program. So first thing is you just draw your modules like a graph on the left, and then you also draw your dependencies like that. And then on the right side, you can have those Lego blocks, and then you can find out some better execution scenarios. For example, in our case, so this was the issue right now, right? And this module actually was about reading the setup for the prover, and especially proven key. We were reading this from the disk. And originally, on the left side, that V5 had issues of parallelization. So we changed these blocks on the left to the right. So we moved that V5 to the early stage of our prover lifecycle, so that the total runtime of T2 became smaller than T1. The other common issue is CPU underutilization. So this has actually many causes, so many root issues. So the first one could be poor parallelization. Second one, synchronization issues and lockup issues. And sometimes you have some blocking I/O operations when you're using disk or a network. So in our case, we had this issue in FFT, and we had synchronization issue in our data structure, so we had to slightly change our data structure so the CPUs are not waiting for other data. So after optimizing CPU, so we changed our CPU usage pattern from left side to the right side. So we got one OK cat is happy. So we got one OK cat for CPU optimization, but we need one more for memory optimization. So let's move to memory optimization. Actually, more than CPU, memory optimization is more important because in general, in most cloud systems or cloud cloud services, memory is more expensive than CPU. For example, you can see that our peak memory usage was 700 gigabytes. And then so we have to use some machine with 970 gigabytes, right? Which is very expensive. But when we can move from this one to the other one with 380 gigabytes, we can save a lot of money. But we can get more cores. So our plan was let's reduce our CPU peak memory to maybe somewhere between somewhere around 380 gigabytes. So the goal is flatten memory usage and memory peak. That's the most important one when you are working on memory optimization. So the first thing we did is using memory pooling. So it means sometimes you have many data structures in your prover, and some data structures are being used hundreds of times or thousands of times. And when you just allocate that data structure every time when you need that, you will allocate that memory, and also sometimes the garbage collector will spend some time to return that memory to the system. So instead of doing that, you just set up this large memory pool for your data structure, and you just allocate that and use it. And when you don't use it, you're not using it anymore, you just return it to the pool, and you keep doing this. So you only allocate once, and you just use it, and you just return it only once. So by using this one, we reduced our memory peak to 450 gigabytes. But still not enough. So we use this mem limit. Most languages, they support this feature. So it's a soft limit of memory peak. So the language, for you, they trigger garbage collection when the memory usage hits this memory limit. So in our case, when you see it here, inside red circle, we have many memory peaks, but that's exactly around 370 gigabytes. So your language or runtime will just run garbage collection, so it will not go up above like 370 gigabytes here. So finally, we were able to move to the smaller machine, but with more cores and cheaper machine. But we found out we are spending too much time in these specific areas because of garbage collection. So we thought maybe we need to do something more. So garbage collection is something that in many garbage collected languages, they just do it for you, right? So it's very convenient, but it's really hard to predict when this will happen. So what if it happens during a very critical tasks or areas of your code? This will be a huge problem. For example, in our code here, so we are doing some FFT inverse function over there, and it's very CPU intensive and memory intensive. So we realized that every time when this part is running, the language runtime try to actually run garbage collection randomly. And because it is really critical in terms of CPU usage and memory usage, it slowed down the whole program a lot. So we realized let's manually garbage collect before entering that critical areas. So we decide to run manual garbage collection before these critical tasks so that we have less context switching overhead inside or during these critical areas. And it actually reduce the runtime a lot. So if you have this kind of issues, you can just manually run garbage collection before those areas, and you will get a lot of improvements. Lastly, so we felt everything's okay, looks good, but sometimes when you have really large input data, you will see sometimes out of memory issue, right? Because we have a very specific size of physical memory, it's not easy to solve that. So sometimes you need to move to a larger machine, very expensive machine with a larger memory, and then you have to run that. But we find out this solution. It's called zkEVM. It's an in-memory swap feature. Most Linux systems have this feature, and you can just turn it on and turn it off. We all know the swap space in storage or disk, right? But it's slow, so in production it's almost hard. It's impossible to use it. But this feature is an in-memory swap. So this one, if you don't have enough memory, this will compress your data inside your memory and will just store that within your memory. So, for example, over there, we have like 740 gigabytes of memory, physical memory. But I set up like 1.5 terabyte of swap space. So you can actually have a lot more memory and a kind of fast swap space in your system. So we are actively using this for massive integration tests with terabytes of memory usage. So finally, we got 2 happy OK cats. And let's talk, I will share quickly one more optimization things. So one thing is data compression. So we realized that the transaction data has really high compression ratio. So if your I/O or network is the bottleneck, you can just compress it. And for example, our case, 40 gigabyte of trace could be 2 gigabyte of trace. And zeroization is a kind of time you spend on initializing your data. So because we are dealing with very large data set and very large data structure, sometimes time taken for initializing your data is a lot. So you might need to auto zeroization supported by your language or use optimized library or low-level libraries for zeroization. So let's conclude the talk. So result, we were so happy, yeah. And then we reduced like ZK-EVM proof of runtime by 75%, which is good. And we saved a lot of operating costs. And not only saving the operating cost, we reinvented that into our previous system. So we increased the finality speed and also higher TPS. And ironically, we were able to understand what we did and what we built and what we are doing, which is, I think, most important one. And some lessons we learned, please do not pre-optimize your code unless you fully understand your code. So I strongly recommend that make optimizations only based on your measurement. And instead of doing this with a kind of a local view, you need someone to have a global view so that you can set priorities for optimizations. Our future work includes distributed ZK-EVM prover, so different modules running on different machines. That means we can use some smaller machines to save cost. And then we are thinking about also how do we accelerate provers. We think optimization is never a one-time task, so please measure, analyze, optimize, and repeat. Thank you.
Amazing. Great presentation, Leo. All right. So remember, you can always ask more questions and vote for the questions that you want it to be answered. So let's start with the first one. How could a fair okay, this is spicy. How could a fair challenge benchmark over same machines and input be organized among ZK-L2s? So like, yeah, how to benchmark up against different systems?
I think it's really hard. Yeah, I think because I explained that in the maybe introduction, because every team or every project has different architecture, different models, based on different cryptography. So I think this is just a good research area. I mean, it hasn't been solved yet. So yeah, it's hard. At least maybe GPU-based, CPU-based, or some specific cryptography-based. It could be benchmarked, but in general, it's really hard. Yeah.
Mm-hmm. Yeah, agreed. Would you recommend on-prem prover or cloud prover?
Right now, I think you can. I think you better start from the cloud-based, because
cloud-based,
especially on the early stage, or especially when you are a small project.
Mm-hmm. Makes sense. If the memory compresses well, then couldn't you instead use more efficient data structures in linear?
Sorry.
Is the top one. If the memory compresses well, then couldn't you instead use more efficient data structures in linear?
Yeah, actually, that's true. We are trying to optimize our data structure as well. Right now, we don't actually compress a data structure in production because to avoid some side effects. But after optimizing a lot and we have too many transactions or too much transactions, I think, yeah, we need to come up with better data structure.
Yeah, as you say, it never ends, right?
Yeah.
Always optimizing. I've read that the finality of Linear is around 8 to 32 hours. Will these improvements allow these to be reduced? And if so, how low can it go?
Actually, the finality time includes many different factors, actually. Not only the prover itself, but number of transactions or service layer agreement or something like that. So it's not only, it doesn't depend on solely on the prover optimization, actually. It's more than that, so.
Yeah, agreed. Have you had examples in where an attempted optimization actually backfire in an unpredictable way?
Yeah, that's true. So I think that mem limit stuff is actually one of them. Without mem limit, the soft memory limit stuff, because that automatically triggering garbage collection for you. We didn't have any issues in global constraints part. But after applying that, we actually got a lot of garbage collection calls within global constraints, and maybe the runtime increased a lot by that. And that was actually a huge issue. And we finally found out, and I fixed it.
Great. Has Linear ZK-EVM thought about switching to zkEVM to further improve performance?
I have no idea on this talk, in this question, so yeah, maybe I'll skip it.
Yeah, let's skip it. Remember, you can always find the speaker after these questions.
We can discuss about it.
Discuss it, and yeah. What are some trade-offs that Linear made in contrast with other ZK-EVMs?
Well, let's say I saw many projects based on GPU or FPGA and hardware accelerated. And we thought starting with the simplest design architecture is the best one, and especially for so that any small project or researchers, they can just simply run our product and then share ideas to be more decentralized. So for a while, we think we're going to keep this design choice, and we'll continuously work on optimization of CPU-based ZK-EVMs and stuff.
Great. And I think we have time for one more. Besides those techniques, did Linear explore hardware acceleration?
Oh, yeah, this question, we are still thinking about it, actually. But maybe at least for a while, until everything's stabilized enough, researched enough, we will keep working on CPU-based.